Okay, so our next speaker is Chris Johnston. I'm going to drive his slides. And so Chris has worked in the field of aerothermodynamics at NASA Langley since 2006 with a focus on shock layer radiative heating. And Chris, are you there?
Yes, I'm here.
Okay, great. Can you see your slides okay?
Yes.
Okay, just let me know when you want me to advance.
All right. Do I have access to a laser pointer or anything in this mode? It's fine if I don't. I just don't.
Probably not. No,
all right, that's fine. All right. So I'll be talking about model validation for the Mars Sample Return Earth Entry System for the aerothermal environments. All right, next slide, please. So I'll start off by providing a brief overview of EES, so that's Earth Entry System for the Mars Sample Return campaign, and the resulting aerothermal challenges that come from this unique mission. This will lead into some aerothermal model validation required because of how unique the aerothermal environments are for this for EES. This will be the bulk of the talk, and this will all lead into kind of the final component, which is the margin assessment on the heating environments. As I'm moving through this, if you go back, sorry, almost had it. As I'm going through this, I'll be hitting on in the red box. I've highlighted 4 kind of key components of this analysis, and I'm just highlighting here because it's the result of research over the past 10 years, and some of this is the first application to a NASA flight project. And very quickly, I'll touch on it here, and then I'll go through them in detail as I get to them in the slide. We'll be using coupled ablation simulations to assess the impact of ablation on heating. So the blowing at the wall and the resulting chemistry from that, it will be accounted for in our simulations that we do the uncertainty analysis on. This uncertainty analysis will be done using this new automatic convective and radiative heating approach developed by Tom West. We'll also be looking at, this will be a woven TPS, which will result in a unique roughness pattern on the surface, and we want to know how this roughness pattern impacts the convective heating. And we're addressing this problem with grid resolved roughness simulation. So where we actually grid the details of the rough surface in our aerothermal simulations. And this is done by Ali Reza Mazahari and Grant Palmer. And finally, the hybrid CFD DSMC simulations for our wake flow analysis. As I'm saying this, I also realized I skipped through the first slide without highlighting the co-authors enough. So this is the result of, can we go back to the first slide, sorry. So I'm presenting on the behalf of the whole joint Langley Ames EES aerothermal team. So this is Grant Palmer, Tahir Gotchin, Chris Naughton, Ali Reza Mazahari, Tom West, Derek Leckie, and Todd White. So yeah, I jumped the gun there. So it is a combination of this team's work. All right, sorry about that. Go back, please, to slide 2. So these are some of the advancements that we'll touch on here. And one of the reasons we had to utilize these is because of the unprecedented reliability requirements for planetary protection for Mars Sample Return Earth Entry systems. So this is not a typical capsule such as Stardust, Genesis, Hayabusa, anything without a crew on it. I mean, so these past Stardust, for example, the requirements on the thermal protection system are not as high. There's not as much risk there. Because we're bringing samples back from Mars, there is a concern that you could contaminate the planet with this Mars dust. So there's restrictions to the point it's almost like having a crewed vehicle. So some very strict requirements in our TPS and aerothermal simulations, which require these more advanced analyses. All right, slide 3, please. Okay, so this is I'm not going to go through this for the sake of brevity. And this is actually, this whole slide package is 6 months old. It's what I had approved. And so this has even changed. So the one part, so this is the Mars Sample Return campaign. The part that's changed here is the fetch rover part, where there will be, actually, we'll use the drones that you see from that Perseverance is flying, similar to that. These drones will pick up the samples, bring them up back to the the SRL vehicle, put them in a rocket, launches, comes back to Earth. And the point of this slide is that we are interested here in the Earth return component. So this is a atmospheric entry at Earth. We're not talking about the Mars entry component. So this is a vehicle coming back from Mars, and because of that, it's coming back relatively fast. And this is one of the reasons we'll have some unique aerothermal environments. So slide 4, please. And I'm talking or presenting this in terms of from the perspective of the aerothermal team. And our objective on the aerothermal team for EES is to provide the aerothermal environments used for EES heat shield design. So I'm not going to be talking about the TPS sizing or design, that's done by the TPS team. But our main objective here is to provide our best estimate of the convective and radiative heating to the surface of the vehicle and the margins associated with that, which are based on uncertainty and other choices. So that is the objective of what I'll be showing here. And what a lot of this, there'll be the nominal aero heating environment, so the nominal convective and radiation. And then we'll put equally as much work into the margin side of things. And I think that will become clear here. So the TPS team takes this and they'll run it through the material response codes. The peak heat flux that we're providing helps guide the material selection. The total integrated heat load helps size the thickness of the TPS. And for brevity as well, I'll be limiting this talk to just the forebody or the heat shield TPS. So this is the front of the vehicle where you get your highest heat flux. Just as much analysis goes into the back shell TPS, although it's lower heat fluxes, it's also a lot thinner TPS and in fact a different TPS material. So just as much work goes there, but we'll limit this talk to the forebody TPS. Slide 5, please. So I hinted that EES is a unique, resulting in unique aerothermal environments. And why is that? The main reason is because it's Earth entry. It's coming in at a much steeper entry flight path angle. And it's doing that because it's not going to have a parachute. And so it has to hit a certain landing spot or basically crash into the ground within a certain area. And so the steeper entry flight path angle allows for a more accurate landing. So that means, so plotted here is in terms of altitude, velocity, space, and these figures are missing the vertical axis, and that's on purpose for export control. So that was not an error in the slide conversion, and you'll see this throughout the talk. So what I'm trying to show here is EES comes in, it reaches lower altitudes at higher velocities, and this results in the higher velocity you are at a lower altitude, the more extreme the aerothermal environment is. So that's one aspect relative to Stardust, Hayabusa, even Apollo missions. It's steeper, denser part of the atmosphere at high velocity. That's one component. The other component is relative to other capsule missions. So other than the crewed Apollo or Orion vehicles, it's much larger than these past capsules, such as Stardust or Hayabusa, and that's shown in the bottom left figure. So the red dashed is EES relative to Hayabusa, for example. It's just a much larger vehicle. And that, again, another reason for that is it helps slow down. So it's because we're crashing into the ground, basically. So the larger vehicle size and this entry trajectory results in the highest peak heat flux of any NASA Earth entry vehicle. It also results in unprecedented levels of roughness and turbulence. So these are some of the primary challenges. So these are getting into regimes that we have not validated our tools for, and that's going to result. That really motivates a lot of the work that's I'll show here in the next few slides. So next slide, please. And here, I'll just breeze through this and I'll talk about the key aspects of this as I'm getting to the components that we're using to validate this. So our nominal environments, kind of our standard approach used for Orion, for example, is pretty much used here. So we'll use our standard NASA codes, DPLR and LoRa, and MAP DSMC for non-continuum conditions. On the DPLR and LoRa side, it will be 11 species, 2 temperature, air chemistry, fully catalytic radiative equilibrium wall. One of the more advanced things here is there is coupled radiation. So the impact of radiation on our flow field energy equations is accounted for. When it comes to the roughness model, I'll talk about this in more detail. It's a simple post-processing step to account for the impact of the rough TPS surface on the heating. this will be a big topic here in a few slides. And the Cebisi-Smith turbulence model is pretty much our best validated model, but this again will be validated as we go through this. And ablation is accounted for in the design process with a commonly used blowing correction. And we will validate this with our coupled ablation simulations. So this is a nominal model, so now our job is to validate or provide experimental validation or higher fidelity approaches to provide confidence that this is a sufficient design approach. So we'll start that here on the next slide. If you can move to slide 7. All right, before we get to that, I'd like to show the magnitude of the different contributors to the, or what physics really dominate the heating environment at the stagnation point, and then on the next slide will be the shoulder, and then I want to show the impact of ablation. So if we just looked at the stagnation point heating through the EES trajectory, it's laminar, of course. You're not getting the impact of turbulence at the stagnation point. So again, so this is 0 degree angle of attack, so stagnation point. So it's basically an axisymmetric flow. So pretty high convective heating, and then radiative heating is not negligible. It's not a dominant contributor either, but it's definitely something you have to account for. So we need some way to validate the convective heating at these levels, and this is dominated by chemistry, a lot of catalytic impact. We want to know the impact of ablation on this environment. So we need experimental validation at these higher velocity conditions. You can't really validate this kind of heating environment on most of our ground-based facilities. You need the energy or the velocity to get the chemistry and all the thermodynamics. So we need to look at flight data for this aspect. If we move to the next slide, it will be slightly different. So here we're looking at the near shoulder, and this is highly impacted by turbulence. So if you look at, we just do the laminar simulation, then we move to the smooth wall turbulence simulation, you see the increase going from blue to red in the heating. We're trusting our turbulence modeling a lot there to get that huge increase. And we get a further pretty significant increase when we account for the impact of surface roughness. So going from the blue all the way to the black, this is where some of our confidence breaks down. We are really going to look to a whole suite of experimental campaigns. This is not as sensitive to the energy. We don't need as much the catalyticity or the thermodynamics of the flow field. This is more of a fluid dynamic phenomenon that we have to understand near the surface. So we need experimental validation data to assess turbulence and roughness augmentation models. One of the unique aspects of this turbulent environment, because of the 45-degree sphere cone, is you get supersonic flow deep into the boundary layer near the roughness heights. There's a risk that you'll get supersonic flow interfering with the surface roughness, and you might get shocklets or some enhanced roughness augmentation due to that. And that is a big fear that we have, and that drives a lot of the work here on the next few slides. If you go to the next slide. All right, the impact of, so all of that what was shown there was without the impact of ablation, so no blowing at the surface. Of course, when we apply the actual vehicle, the TPS, which is an ablating, charring ablator, will be blowing from the surface, introducing carbon and hydrogen species, and we want to have some way to simulate that in detail, and that is done with the coupled ablation simulations within the design approaches. It applies actually the blowing correction within Fiat, and we want to show that this is conservative. But then this shows the magnitude of going from the no ablation in black down to the green. So there's a significant impact of ablation, and we want to have confidence that we're not being non-conservative when we apply the design approach. So we're looking for experimental data here as well. If you go to the next slide. So the next step, I'll briefly go through how the model validation now for each of these components. Go to the next slide. And we've broken it up into basically the couple slides I just went through are the different rows. So the laminar stagnation region, the rough turbulent heating. We want data that captures this supersonic flow near the roughness heights, and we want data that also has the impact of blowing. And we have a suite of different experiments listed in the different columns. So the first two of these are flight data, the rest are ground-based data. We also have a planned test in the Langley Mach 6 facility. But wherever the green box is, it captures those physics so it's relevant to that phenomenon that we're trying to address. So in a perfect world, one experiment would be green for all the different rows, but of course none of them are. We're really lacking in measurements where we have supersonic flow near the roughness height. You see just this one Holden measurement listed here, in our planned Mach 6 test will capture that. And we don't have many experiments that capture the impact of blowing on the heating at these kind of conditions either. In addition to the experimental validation, we also are providing some level of validation with just simply higher fidelity simulations. So one of these are the coupled ablation simulations I discussed. The other is grid resolved roughness simulations that I had mentioned at the beginning of the talk that Alireza and Grant are working on. So this is where we actually grid the roughness, and this gives us some insight into making sure that the design approaches are conservative. So next slide, please. I realize I don't have much time here, so I'm going to skip through some of this. So just as an example of how the matrix on the previous slide, if we just take some of that, the roughness augmentation part of that, we analyzed all the different data, plotted here. We compare it with our design approach, make sure our margin's capturing that. And whatever our margin doesn't capture, we choose our margin to capture all of this data. And here, the largest difference is this 17% listed in the top right. And we bring this into our this will show up in our margin assessment. If you go to the next slide. And here's an example of the grid resolved roughness I mentioned. So on the left is an example of the TPS scan surface, and that is gridded up to the, we grid a portion of the flow field as shown on the right, and this is possible because of the axisymmetric baseline flow. It's also possible because we have a patterned roughness surface, so it's not a perfect representation, but it captures the most important flow features. And this is a work in progress, and Alireza, it even has the impact of ablation in here. So we have these simulations with blowing, with ablation products, the interaction of roughness. So all the physics are there. We can compare the result of that with our lower fidelity design approach. So it's very useful. Next slide. I'll skip this as coupled ablation. So this just shows the impact of coupled ablation. It shows that our design approach is conservative. Next slide, please. So all this feeds into the margin assessment. Next slide, please. And this will be a RSS of an experimental component, which is a result of that huge matrix of different experimental campaigns. And then we have a parametric uncertainty component. We RSS the two to get the margin. We do this at every point on the flow field and at different trajectory points. So it's both a spatially and trajectory dependent margin. Next slide, please. And so going through all the different data we had shown here, we found the worst agreement. We choose a multiplier that captures both of the stagnation point and the near shoulder. And this gives us our experimental component, which varies from the stagnation point to the shoulder based on just a simple blending function. So we go from a 38% to 33%, which is the result of all this data. Next slide, please. And the other component is the parametric uncertainty analysis. So we take our coupled ablation, smooth wall, coupled ablation simulation, and run it through this, what we call the LoRa-UQ approach, which was developed by Tom West, which is a parametric uncertainty analysis based on this polynomial chaos approach, which accounts for uncertainties in our range of modeling parameters, such as flow field kinetics, diffusion cross sections, turbulence Schmidt number. So there's many parameters listed there. And we should get the resulting parametric uncertainty on the convective and radiative heating. Next slide. And here's just an example. So lots of parameters go into this. Next slide, please. And here's just a result for some examples. We get a convective uncertainty bounds. And we use these, if you go to the next slide, I'm sorry to go through this fast. We combine the parametric and the experimental component along the surface. So here's just at one point along the radial location, we have a surface-dependent margin. We do this for a range of cases in our database. This gives us this higher fidelity margin approach, which we can go back to, and we have traceability for what produced the margin and what experiments produced it, or what modeling components we're driving that. We can go back and refine this, and we're currently in the process of looking to reduce this margin. So it ranges from 33 to 52%. So next slide is my conclusion. I think I'm out of time. So yeah, so that is how we're attacking this EES aerothermal environment and margin. So again, this is a pretty unique environment. We're attacking it pretty much in a couple different directions, from this experimental approach, from looking at a range of experimental data, to coupled ablation simulations, to these grid resolve roughness simulations, and getting this all down and using it in our margin assessment. We're trying to utilize a lot of past research efforts that have been done in NASA.